Hello everyone, I'm your instructor, Wang Shengda. In this lesson, we will study the factors affecting polymer crystallization ability. Through this lesson, you will understand how factors such as chain symmetry and regularity, copolymer sequence structure, degree of branching and cross-linking, and intermolecular forces affect polymer crystallization ability. You will be able to assess the polymer's crystallization ability based on its structural formula and chain structure, and assess the strength of its crystallization ability. The crystallization ability of polymers varies. Some polymers can always crystallize. For example, polyethylene and polytetrafluoroethylene. Some polymers can crystallize under certain conditions, while under other conditions they cannot crystallize. Some polymers cannot crystallize at all. For instance, atactic polystyrene. So, how do we assess the crystallization ability of polymers? To assess a polymer's crystallization ability, you must understand the factors affecting polymer crystallization ability. These factors include chain symmetry, chain regularity, copolymer sequence structure, degree of branching and cross-linking, and intermolecular forces. The first factor is chain symmetry. The more symmetric the polymer chain is, the better the chain flexibility, and the easier the polymer is to crystallize. For example, polyethylene and polytetrafluoroethylene both have excellent chain symmetry along the main chain direction and perpendicular to the repeating unit direction. Polyethylene's crystallinity can reach over 95%. The crystallinity of polytetrafluoroethylene can reach 90% to 96%. Due to their strong crystallization ability, it is impossible to obtain fully amorphous polyethylene and polytetrafluoroethylene. Additionally, polymers such as polyisobutene, polyformaldehyde, and polyethylene terephthalate exhibit high crystallization ability due to their high chain symmetry. They have good crystallization ability. The second factor is chain regularity. For asymmetric polymers, the higher the chain regularity, the stronger the crystallization ability. This is because crystallization is the ordered arrangement of microscopic units. The stronger the internal order of the microscopic units, the easier it is to arrange them in an ordered manner, and crystallization becomes easier. The first case is the presence of optical or chiral isomerism, in the polymer. The crystallization ability of polymers with different optical isomeric units varies. Taking polypropylene as an example, isotactic and syndiatactic polypropylene can crystallize, with isotactic polypropylene having stronger crystallization ability. Atactic polypropylene has no chain regularity, and thus cannot crystallize. Let's summarize. In general, both the isotactic and syndiatactic forms of the same polymer can crystallize, with the isotactic form crystallizing more effectively. Atactic polymers cannot crystallize. However, there are some exceptions. For example, atactic polyfluoroethylene and atactic polyvinyl alcohol also have strong crystallization ability. This is because the size of fluorine atoms and hydroxyl groups is similar to that of hydrogen atoms. This results in these two polymers having chain symmetry similar to that of polyethylene. The second case is the presence of geometric isomerism, or cis-trans isomerism in polymers. Take poly-1,4-butadiene as an example. The molecular chain structure of cis-1,4-polybutadiene is relatively irregular. The intermolecular distance is relatively large. Its crystallization ability is relatively weak. At room temperature, it is a rubber with excellent elasticity. On the other hand, trans-1,4-polybutadiene has a more regular molecular chain structure. It crystallizes more easily. At room temperature, it is a plastic with poor elasticity. The third factor is copolymerization. Copolymerization mainly affects chain regularity. Taking polyethylene and polypropylene as examples. Polyethylene and isotactic polypropylene have high crystallization ability due to their high chain symmetry and regularity. Their crystallization ability is very strong. At room temperature, they are high-performance plastics. When ethylene and propylene are copolymerized to form block copolymers, the chain regularity is reduced. The crystallinity is significantly lower than that of the individual homopolymers. When ethylene and propylene copolymerize to form a random copolymer, the chain regularity completely disappears. As a result, the crystallization ability also disappears. At room temperature, it is a high-performance rubber. The fourth factor is the degree of branching and cross-linking. The more branching or the higher the cross-linking degree, the weaker the polymer's crystallization ability, until it can no longer crystallize. This is because branching and cross-linking disrupt both the chain symmetry and chain regularity. Additionally, they affect the flexibility of the polymer chains. For example, high-density polyethylene has better crystallization ability than low-density polyethylene. This is because low-density polyethylene has many branches in its structure, which disrupts the chain symmetry and regularity. The fifth factor is intermolecular forces. The greater the intermolecular forces, the worse the chain flexibility. However, they can sometimes inhibit crystallization, and at other times, they can promote crystallization. For polymers with intermolecular hydrogen bonds, such as polyamide, the presence of hydrogen bonds helps arrange the molecules in an ordered fashion, thus promoting crystallization. This results in a crystallinity of 50% for nylon 6 and nylon 66. In the case where there are no hydrogen bonds between molecules, excessive intermolecular forces hinder molecular motion, making it difficult to achieve ordered arrangement. This weakens the polymer's crystallization ability, until crystallization becomes impossible. The last factor is chain flexibility. In fact, the previously mentioned factors of chain symmetry, branching, cross-linking, and intermolecular forces are all related to chain flexibility. They are just more specific. Chain flexibility is essential for crystallization. The better the chain flexibility, the easier it is for chain segments to align in an ordered arrangement. This makes crystallization easier. For example, polyethylene chains are more flexible than the chains of polyethylene terephthalate. The chains of polyethylene terephthalate are more flexible than those of polycarbonate. This is because the number of benzene rings in these polymers increases. As a result, the chain flexibility decreases. Therefore, the crystallization ability decreases in the following order: polyethylene, polyethylene terephthalate, and polycarbonate. However, there are exceptions to the effect of chain flexibility on polymer crystallization ability. When flexibility is too high, the molecular chains can easily align into the crystal lattice, but they can also easily detach from the lattice. In practice, they cannot crystallize. For example, polydimethylsiloxane has chains that are too flexible to crystallize. It is a high-performance rubber. In contrast, polyethylene chains are not as flexible and crystallize more easily. At room temperature, it is a high-performance plastic. In this lesson, we studied the factors affecting polymer crystallization ability. The higher the chain symmetry, the stronger the crystallization ability. The higher the chain regularity, the stronger the crystallization ability. The crystallization ability of copolymers is generally weaker, because it disrupts the chain regularity. The higher the degree of branching and cross-linking, the weaker the crystallization ability. Intermolecular forces sometimes promote crystallization, and sometimes hinder it. The higher the chain flexibility, the stronger the crystallization ability. Polydimethylsiloxane is an exception. As we can see, chain symmetry, branching, and cross-linking, intermolecular forces, and chain flexibility are all related. Copolymers are related to chain regularity. Therefore, you can focus on chain flexibility and chain regularity to remember the concepts learned in this lesson.